Welcome to Hot Chips 2025. Session 3, Graphics.
Hey everyone, now following the keynote, it's time for our graphics session. So we have three very interesting talks in this session. The first one is a talk from AMD on their graphics GPU. We have two speakers for this talk. The first one is Andy Pomianowski, who leads the product architecture for the last three generations of AMD's discrete graphics products. The second speaker for the same talk is Pappu, who's worked on client and GPU SoCs for the last several years, and he's now working on the data center GPU at AMD. So over to our speakers.
Okay, so thank you very much, and thank you to Hot Chips for having us here. My name is Andy, and I lead advanced architecture for Radeon graphics at AMD. And as was stated, I also led the product architecture for the last three generations of our Radeon graphics processors. So it's a great pleasure for me to be here today with my colleague Lax to talk a bit about RDNA 4 and what we did, and to really present the work of a large team in the background. And it's my privilege to be here to present all of that work to you today. So when we began thinking about RDNA 4, the vision for it, what we were going to do, we were, as you might expect, very, very focused on the needs of our gaming community. And to create a good architecture for gaming requires you to understand what the workloads are that you've got today and the workloads you're going to see for the next 5 years in the future. So we were trying to drive a lot of efficiency in the rasterization and compute workloads that are at the heart of gaming today. But we're also looking forwards, and ray tracing, some of you may be aware of how popular ray tracing is starting to become, and we're also now seeing ML affecting everything, and discrete GPUs are no different. And ML techniques are coming in, will start to become very popular, we think, over time. So if you look at the chart on the right here, you'll see across a few metrics how our progress has been over the last few generations. You know, starting with RDNA 2, with RDNA 3, we pushed performance forward quite significantly, but RDNA 4 really represents a large leap in efficiency and a huge leap in ray tracing and ML efficiency. So I'll talk a bit about how we achieved that in a minute. So on top of this, we have to actually feed the core as well. So we did improvements outside the core in our compression. So we've enhanced our capabilities for all workloads there so that we can keep feeding the core. And we also look at the needs of our streaming community who stream games, our content creators. So we updated our media and display engines as well. So RDNA 4, here's an example of RDNA 4 architecture. This is our Radeon 9070 XT processor. And the way in which we build these is we have our workgroup processors, which are the core of our compute capabilities. And within these, we have our core compute, plus also ray tracing and ML acceleration. And we'll talk in more detail about that later. We group these into shader engines. The shader engines represent clusters of these workgroup processors to which we dispatch work. That could be geometry shaders, pixel shaders, compute shaders. So they basically are our work distribution. We farm out these necessary shader work to these shader engines. And we have them clustered around a centralized L2 cache for low latency. That L2 cache, we grew it this generation because what we saw was that challenging workloads like ray tracing, like having more local cache. And so by building out that level 2 cache, we were preparing the architecture better for ray tracing workloads. And we'll talk a lot about those in a bit. On top of that, what we also have is our third generation of our Infinity cache, which provides bandwidth amplification for the core. And we have a GDDR6 memory interface backing that. And between the two of them and our new compression techniques that we developed, these provide ample bandwidth to keep the core fed and to provide high performance in the latest gaming applications. On the multimedia side, we improved our media engines. We have a dual media engine in the 9070 XT, and I'll talk a little bit about that on the next slide. And actually putting pixels on the screen is the responsibility of our Radiance display engine, and I'll have a little bit on that as well. The part itself was fabricated on TSMC's 4nm technology, and it communicates with the host over a PCIe Gen 5 interface, 16 lanes. So let's talk a little bit about the media and display capabilities, kind of starting at the outside, and we'll work back into the core. So we have this dual media engine in the 9070 XT. Our goal here was, again, to look at the needs of our streaming, of people doing streaming, content creation, improve our low latency encode from the media engines. So we made some big strides in our H.264 encoding by concentrating on how the bits were allocated to the stream. We've been able to deliver significantly higher detail preservation, and also we've reduced the amount of blocking artifacts that you get. Now, on the newer codecs, which are intrinsically higher quality than H.264, that doesn't mean that they didn't need work as well. So we've improved the quality of both H.265, and we also added B-frame support to AV1. So taken all together, we've produced quite a comprehensive package of improvements for our streaming and content creation communities. On top of this, we also have a significant advantage here in low-power video playback, because by increasing the performance of these engines, what happens is they get through the video decoding much more quickly, and we've also optimized their memory traffic to the DRAM. So by doing this, we're able to race to idle, reduce the power consumption when you're doing media playback. And on that same note, looking at idle power consumption when you've got multiple displays, we take advantage of the latest FreeSync displays with variable refresh rate to minimize the idle power with multiple display configurations. On the back end, in the display engine, we also integrated our Radeon image sharpening filter for the first time into the back end. And that allows that sharpening filter to be applied at the click of a button to any gaming experiences you're having, and also even to the desktop. Okay, so now we've moved out from the back end, and we'll move right into the heart of the architecture. So at the heart of RDNA 4 is the workgroup processor. And this is logically similar to how it was in RDNA 3. We have two compute engines, which have ray accelerators and ML accelerators attached to them. They communicate, and they have a shared local data store that can be used for bandwidth amplification and to hold data that's common across the wave. We've made a few additional changes I'll touch on here to drive up performance. We'll talk about the ray tracing and ML in more detail, but in the scalar units, which do perform operations which are common across an entire wave, we added floating point support to those, which means that floating point calculations which are common across the wave, we can move them onto those scalar units, improving performance and saving power. We also added support for split barriers. So in this case, what happens is when the barrier is signaled, work that's not related to the barrier can continue, and you can continue doing useful work while waiting for the barrier to be actually satisfied. So we've made a few underlying changes here to kind of adapt the core more for the future-looking workloads that we have. So now let's take a look at ray tracing in detail. So at the top level, ray tracing operates by shooting rays into a data structure that contains all of the geometry of the scene. It's called the bounding volume hierarchy. It consists of bounding boxes which contain the triangle geometry data for the scene. And in RDNA 4, we've taken a fairly comprehensive approach to improving this. We doubled the throughput by adding another intersection engine. So we do 8 ray box and 2 ray triangle intersections per clock now. And in addition to this, we added a dedicated transform engine. When you go from the top levels of the bounding volume hierarchy, when you go from the bottom levels, rather, of the bounding volume hierarchy into the top levels where you have the geometry, top levels to bottom levels, I'm getting those backwards. So you go from the top levels to the bottom levels have the geometry. And when you do that, you have to do a transform, because you have all the instances of the geometry down at the bottom levels. That used to happen in shader code. We added a dedicated engine to offload that. We also store our ray stack in our local data share. And when we are we have to push and pop rays from that stack to be traversed, and we added dedicated instructions to reduce the overhead for those operations as well. We went from a 4-wide, so each child node would have each node would have 4 child nodes. We went from that to an 8-wide structure. And this has 2 effects. It flattens the BVH, which means we take less steps to traverse array through the tree. And it also, by going to these wider structures, we provide the data that's needed by those doubled intersection engines. Now, we also compressed the nodes more. You can see in this chart on the right, the same tree being expressed the way we did on RDNA 3 and RDNA 4. RDNA 4 is much more compact, and obviously that helps with our memory capacity, but also with memory bandwidth during traversal. Now, we also added a new enhancement that's called oriented bounding boxes, and I'm going to spend a slide on that in a minute. When you make the traversal this much faster, you have to accelerate the shading as well. You traverse all these rays through, and then you've got to shade the results that you get back. And so what we're doing there is we've got a couple of new features. Firstly, we have a relaxed ordering for memory. I'll have a dedicated slide on that. And we also introduced a new feature for dynamic register allocation. And I'll also go into that in detail. So let's start with the oriented bounding boxes. What are they? The clue is in the name. When you hold this geometry in the acceleration structure, what happens is you have these bounding boxes, which are basically volumes, and they have X, Y, and Z extents. And inside those, you'll have finer boxes, and eventually you'll get all the way to the triangle data. But these are 3D objects in a world. So those extents are aligned with the axes of the world. What happens if you have geometry that's not well aligned with the axes of the world? Well, what happens is the boxes have to grow. And I'll show you an example here. This is simplifying it to 2 dimensions. But if you think about this top box, what's happened is I've got a triangle in it, and it's not aligned with the axes. And so that triangle is occupying a small amount of that bounding box volume, and the rest is empty space. So any ray that came in and intersected that bounding box is likely to, it has to be tested against the triangle, but it's almost certainly going to miss because most of that volume is empty. But what if, instead of having these boxes aligned, you could rotate them? You could change their alignment. Then they could bound the geometry much more tightly, and that's what you see in this bottom diagram where we've simply rotated the box, and now you've got much less empty space. You're not going to get false positives so often. So how do we do this? Well, we need a compact representation of the possible rotations. So with each box, we store a octahedral mapping of possible rotations. We have these mapped onto this octahedron. It allows us to encode the possible rotations in a very compact space, because obviously we need this in every box. And then a ray coming into a box is transformed via that rotation and then continues to traverse. And by doing that, we can achieve this result that we showed with the boxes being oriented to really tightly bound the underlying geometry. And what's the effect of this? Well, I'm showing a heat map here. The heat map at the bottom uses OBBs. The heat map at the top does not. And what you'll see is, overall, the general heat is significantly reduced, but particularly in very difficult areas of the geometry that are not well angled with respect to the world. In this case, what you have is you have a ladder on a fire truck, I believe it is, and it's kind of going across the street. And you can see this huge intersection load that occurs whenever any rays go near that ladder. But when we apply the OBBs and we align them to this ladder, that cools down completely, and we waste much less time with false positives. Okay, so that's the OBBs. Now let's take a look at the outer order memory. So memory requests go into a queue. And on RDNA 3, we had a very strictly ordered queue. So requests that were made later in time were not allowed to pass requests made earlier in time. And this is important because if you have requests hitting in cache, they'll be satisfied very quickly. If you have requests going to memory, they take a long time. And on a lot of earlier workloads that were very well behaved, you have traditional rasterization workloads, compute workloads, generally this would not be an issue. But ray tracing is extremely divergent, and you tend to get a lot of misses when you get down into the low levels of that acceleration structure. And we observed that this was causing efficiency losses. So what we did in RDNA 4 is we added out-of-order queues. So we now allow some requests, provided they're independent, to pass other requests in time so that we can keep work going on the machine more effectively. So what does this look like? If we look at the diagram on the top right, we're kind of symbolizing two different waves running on the machine simultaneously. And one of them is lucky, and all of its requests hit in cache. It sends out 5 requests, they're all going to hit. The other one is a lot less lucky, and 3 of its 4 requests are going to miss. So what does this look like when you're in a strict ordered situation? Well, what happens is the first wave gets its first request off fine, but then its second one comes after that first miss from that second wave, and then it gets held up. And once that miss comes back, then it can proceed forward again. It gets another couple of requests out, but then a second miss comes in, it gets held up again. And so by the time it finishes, what's happened is that wave that was getting lucky got held up significantly by the one that was unlucky. So in RDNA 4, what happens when you allow these to proceed out of order? Well, what happens is you find that that lucky wave gets to get its work done and get off the machine very quickly. You can't do anything about that unlucky one. You know, it's going to have to do those. But the lucky one gets off the machine quickly. That means we can get more new work onto the machine, and that new work can then proceed, and that allows us to drive efficiency up in these difficult situations. So what do we see overall when we look at the gains that we've got from the rate traversal architecture in RDNA 4? If we take it broadly and look across kind of a huge range of different workloads that we've fed into the machine, what you see is for each compute unit, we're delivering about twice the throughput that we did in RDNA 3, which is a very significant uplift. And you know, this breakdown chart on the right kind of shows how that's being distributed between these different improvements we made. So the largest improvement you can see comes from that doubled up ray intersection capability and the wider BVH. But we also get incremental improvements on top of this from all of the other changes that we made in the architecture. And the important thing here was that just doubling up that BVH throughput, under certain circumstances, like we get a whole load of badly oriented bounding boxes, or we're getting a lot of these bad memory requests, that would eat into that performance gain. So we wanted to build a really robust architecture. And by bringing all of these improvements together, we've delivered something that consistently outperforms RDNA 3 by a significant amount on ray tracing. And you know, the exact contributions of these different capabilities we put in will be revealed in different workloads, different scenes that come through. But the 2x is really kind of easily measured, I think, if people have access to these and they can see the ray tracing advances that we've made. And you know, we think we really put together a good package here for consistent ray tracing performance. There was one piece left that I hadn't talked about yet, and that was the dynamic register allocation that we included. So this again came out of observing ray tracing workloads and what we were seeing there. Ray tracing workloads tend to have 2 phases in their shaders. First, you have a phase where you are actually tracing the rays through the BVH structure, and then you have a phase where you have to shade the results that came back. You've got your intersection, what does the material look like? And they're very different. The traversal normally uses very few registers. But at the end, when you need to do the material shading, these are complex materials, and you have a lot of live registers. And so on RDNA 3, what would happen is you'd launch the work, and it would need to allocate the worst case number of registers. So that's the registers that are going to be used during the material shading. And this limits the amount of parallel work you can get onto the machine. So in this sort of simplified diagram here at the top right, you can see that quite a lot of the time, a lot of the registers are not being used by these 3 threads going on the machine, but it's always allocated for the worst case. So we're only able to get 3 waves in flight here. Now on RDNA 4, we introduced a new capability to allow registers to be allocated dynamically. The shader can request registers from a pool when it needs them, and it can release them back to the pool when it's done with them. So this is handled by our shader compiler transparently in the background. You know, it breaks down the shader into these places where it wants to get more registers or give them back. It handles the cases, you know, you have to make sure that you can do forward progress if you're dealing with dynamic allocations on the machine. And so what you see is that without increasing the size of these register files, which are very expensive, we're able to get more work in flight on the machine in parallel, and this improves our ability to handle memory latency during ray tracing. It allows us to operate more efficiently on the machine, And in this case, shown at the bottom, this is just a sort of simplified diagram, but you can see that by allocating these registers and deallocating them, we're able to squeeze another wave onto the machine. We now can get 4 on the machine instead of 3 with the same number of registers. So this can be used in multiple places, but ray tracing is really the example workload that drove us to add this new architecture. So moving on from ray tracing now and talking about ML for a bit, what we have here is the ML capabilities are significantly enhanced. You know, ML is touching everything we do. So we added global load operations that can load and transpose matrix data on the way in. We've also significantly improved the overall throughput by adding multiple new pipes for the different math operations. So we've driven up the rates for low precision operations, particularly by adding FP8 capabilities to the machine. And so when you saw that diagram earlier that showed a 2x performance from RDNA 3 to RDNA 4, that was a like for like. But when we actually use the capabilities of RDNA 4, we can deliver much higher improvements, 4x improvements, when we can move things onto these lower precision formats that are increasingly being used. And beyond that, we also have support for structured sparsity. This requires networks to be trained in a specific way where you know that certain of the weights are going to be effectively zero, so you can ignore the computation. But that allows another doubling if you've done that. So potentially you can even get to 8x. And we use the capabilities of the new math pipes in things like our FSR4 that we shipped recently. So I'll wrap up by bringing everything together in a single example, ray tracing versus path tracing as we think in the future, and how do we bring all these capabilities together. With ray tracing, you shoot rays into the scene, you get visibility, you might get reflections, you might then shoot rays to see what your lighting is like, you might shoot a shadow ray to see if you're lit or not, and then you can scale those capabilities up across multiple different many lights or however you want to do it to generate a scene. You shoot rays for every pixel and you kind of generate these results. Path tracing is different. Path tracing, we're trying to sample the entire scene and all the possible paths of light that can take. So you do this by shooting a lot of rays, and you kind of send them out in random directions through the scene. Each takes a random bounce, and when it arrives at a light, it can propagate that back. This is very expensive, but it can solve all of light transport, all of the ways in which light travels through a scene to get to the eye. And so this is attractive, very attractive, but it's extremely expensive. It wouldn't be practical on modern hardware, even with all the ray tracing acceleration we put in. So how do we bring all the capabilities together? In RDNA 4, this is an example of a 1 sample per pixel path trace of a scene. And you can see it's mostly just noise. Some rays are going to arrive at light sources and they're going to look good, but everything else is just going to not contribute to the scene. So how can we improve this with all the capabilities of RDNA 4? We bring in the neural techniques. And we also bring in advanced ways of sampling. We start with a light sampler that that chooses which rays to shoot a bit more carefully. We then add on a neural network called neural radiance caching. And so this runs all the time, and it trains itself from frame to frame. And it's producing an approximation of what you would see if you fired many more rays, and also what you would do if you had a lot of bounces through the scene. But even this wouldn't be enough by itself. So what we have to add then is neural supersampling and denoising. This goes from what's still a noisy image to a stable, high-resolution, highly detailed image like you see here. And this brings together all of the capabilities of RDNA 4 to produce an image of this quality. And hopefully that gives you a good idea of what you might see in the future. So with that, I think that wraps me up, and I would like to hand over to Lax to talk about the SoC architecture.
Thank you very much, Andy, for a cogent overview of the innovative ray tracing, path tracing, and memory latency and other component engine features. Good afternoon, ladies and gentlemen. I'm Lax Pappu. Currently, I'm working as an SoC architect for AMD Instinct data center GPU products. Earlier, I led the SoC architecture for RDNA 4 and its follow-on series. RDNA 4 is already in the market, and follow-on series will be in the market sometime later. In this architecture, there are 4 shared engines and 64 compute units. Various graphics clients through the level 1 arbiters and level 1 caches funnel the traffic into a SoC level GL2 a level 2 compute side cache. Infinity Fabric connects GL2 to a lot of SoC components, including coherency stations and last level memory controllers, and GDDR6 memory controllers, and GDDR6 This fabric furnishes a bandwidth of up to 1 kilobytes per clock and operates between 1.5 to 2.5 gigahertz and supports DVFS, dynamic voltage frequency scaling. A 256 bits of a GDDR6 memory operating up to 20 gigatransfers per second provides required memory bandwidth for the gaming intensive workloads. We have built a structurally modular RDNA 4. If you cut the die across that red line, you can create a new SKU with minimal effort. At AMD, we create a lot of products with chiplets. But for this class of machines, given the performance requirements, given the package and assembly turnaround times, knowing the cost, for this size of the graphics engine, we found that going the monolithic way is the right option. Security is very critical in SoCs. Various signed firmware components and locally, privately built buses between the microcontrollers and the critical blocks and the protected register access mechanisms provide the required data integrity. HDCP, high bandwidth digital content protection, and DRM, digital rights management, are some of the critical features, security features worth mention. And RAS is very important, reliability, availability, and serviceability. Whenever a poison is detected by any critical component in the circuit, the newly incorporated driver-level software components will reinitialize the relevant portion of the SoC for a recovery, thus preventing the platform from shutting down. A salient feature of this architecture is centralized compression and decompression. You see that a lot of blocks have incorporated graphics clients, these blocks, such as color buffers, depth buffers, command processors, and shader engines. These are also incorporated in the SoC blocks, such as last level cache controllers and display engine and video encoder and decoders. Since this entire block is implemented in the hardware, it obviates the necessity for any need for software to be cognizant of the implementation details and lack thereof for any need for interaction. Now, with this feature incorporated, we have noticed that up to a 25% memory bandwidth reduction, which also resulted in about a 15% performance overall improvement. A second order benefit of this particular feature is reduced SoC clock frequencies, hence also reduced dynamic switching capacitance, and that is resulted in reduced platform power. RDNA 4 SoC architecture offers a flexible configurability. The markings that you see on this diagram show multitude of options one could fuse of components. Fusing of can be done for a small compute engine, fusing of can be done for entire shader engine, or fusing of can be done for a lot of components in the SoC, including coherency stations, last level cache controllers, and GDDR6 memory controllers, and GDDR6 PHYs. The market requirements dictate the exact configuration we choose from this flexibility. Now, based on the flexibility I have delineated, fusing of flexibility, and a lot of supporting SoC features, which have to be existing along with them, multiple viable SKUs can be derived. The ones shown here are some of those possibilities. As you notice, across the various product SKUs, some of them, all these are being in the market, will be in the market, or they'll be in the market, that the CUs range from all the way from 64 to 28. And your shader engines vary from 4 to 2. And your GDDR6 size ranges from 256 bits to 128 bits. And your memory capacity that is required, supported by this architecture, ranges from 32 gigabytes to 8 gigabytes. And the overall platform power ranges from 304 watts to around 132 watts. A wide range of plethora of opportunities are possible. There are many more viable SKUs possible, but these are the ones the BU found them to be most viable. In summary, RDNA 4 is built for the next generation of gaming and content creation with high-performance ray tracing and ML. Advanced compute capabilities, along with and highly innovative ray tracing and memory-enhanced ML upscaling are some of the salient features in this particular architecture. This architecture also supports a memory capacity that is built to meet the most demanding graphics workloads. Advanced video encoding, decoding, streaming for the media and productivity and content creation are some of the features that are ensconced in this architecture. In summary, RDNA 4 is built for the next generation from all the innovative features we have incorporated, and it is structurally modular. RDNA 4 architecture is a flexible configurability and you can derive multiple SKUs from this product. It is secure, and it has abundance of RAS. I, along with my colleagues at AMD, architected it and built this product. There are a lot of other people who had helped me and my team, and it's my privilege to represent all of them here. Thank you all.
Thank you for the talk. We're running a little low on time, so we could take 2 questions. We'll take one from Slack.
Okay, this one's for Andy then. The question was, the memory ordering that you allowed to pass in this particular version, was that constraint coming from the load store queue, or was it more constraints on when you were missing in memory?
So obviously requests go through multiple layers of the hierarchy. They go into the load and store queues are kind of separate. But so when you make any request, I mean, we have multiple paths to memory. We have a path that goes through texture fetching. We have a path that loads from buffers. But the key thing here was to not allow waves to interfere with each other. So by allowing the different waves to not interfere was the key piece. I'm not sure that I necessarily caught exactly the question, but yeah, the queues are simply the waves effectively have their own queue, provided they're not accessing the same memory.
Thank you. We'll take one from the room.
Me?
Yeah. Can you please introduce yourself?
Dinesh for Nordic Semiconductor. So about 10 years ago, I think AMD was the first to bring HBM into like consumer discrete GPUs. So we obviously see HBM being used in more like enterprise uses, but I wonder if, other than cost, is there a practical reason why we don't see HBM used anymore in like consumer grade GPUs?
No, I mean, I don't think there's a practical, I mean, the memory is memory, right? So we're always looking at what is the most applicable memory to the various different products that we make. And GDDR6 was our decision for this. Okay. But architecturally, you could use different memory.
But like, my question is that it seems like it's not only AMD, it's like the other GPU providers are also not using HBM, so I'm wondering if like there's something underlying other than the cost issue.
Yeah.
Well, you'll just find that everybody is looking at the same environment and making similar decisions. Like.
So if I add something to that, right? So
also, to interject, maybe we can take this discussion up on Slack or during the break. The speakers will hang out during the break for you to.
Sounds good.
Okay. Thank you.
Thank you.
Thank you. Now, on to the next talk on neural rendering. The speaker for this talk is Marc Blackstein, who's been at Nvidia ever since after the first CUDA GPU was launched. And during his time at Nvidia, he's overseen the performance modeling as well as characterization of GeForce, Tegra, and RTX GPUs. So over to Marc.
Clicker. Okay. This is forward? No. This is forward. Got it. Hello. All right. So let's start with a little history. So all of these breakthroughs in deep learning that we've seen over the past 2 decades have been made possible by hardware. And also, it's the hardware that's limiting our progress today. This was Bill Dalley's keynote at Hot Chips a couple of years ago, and I just wanted to start with that point. There are 2 scaling laws, right, that are really important here, right, and they're following different trend lines. The first scaling law is the scaling law of general intelligence, which shows no signs of slowing down. And the other is Moore's law, which appears to be flattening out. With these two in conflict, it's obvious that architecture really matters. CUDA is NVIDIA's universal architecture, software architecture for accelerated computing and AI. And it's been present on every GPU from mobile to data center that we've shipped since 2006. And it enables students and academics and industry and developers to speak the same language and arrive at the next breakthroughs. In terms of compute, it's obvious that compute density has drastically outpaced Moore's law scaling, what it would have predicted. And this has come from a variety of ways, through sparsity, through new ISA, through lower precision formats, and through a lot of work on architectural efficiency. And in tandem with these compute improvements, it was really important that we would pair it with memory and networking technologies that could keep this compute fed. And so there were a lot of breakthroughs along the way there too. In 2018, NVIDIA made a bet that real-time graphics, that real-time inference, would see the same benefits from deep learning that we were seeing in these non-real-time spaces. We shipped our first RTX GPUs with the first generation ray tracing cores and tensor cores in the bet that this would take off. And shortly thereafter, in 2019, real-time graphics had its AlexNet moment, and we called it DLSS. So we fast forward to 2025. It's an exciting time, and I'm here to talk about the Blackwell architecture, a unified architecture from desktop to data center, and it's our most efficient AI architecture to date. So a little bit about, let's start with the big Blackwell, right? And so at NVIDIA, anytime we're sitting down to think through the next generation, we always start with the big problems, with the ecosystem problems. Where is the 10x? Where's the big thing to go after? And in data center, it's really about data center scale computing, right? Treating the data center as one unified block. And we do that through two strategies, right? One, we scale up, and we scale up each generation by focusing on improving the GPU core and the density of compute and memory, and then combining that with more connectivity through NVLink. And in GB300 NVLink 72, we're able to take an entire rack and connect it together in one coherent domain so that it can appear to the programmer and in a performant way as if it was one virtual GPU. And so that's our scale up in the Blackwell. And for scale out, we use NVIDIA Spectrum-X Ethernet technology, and that'll be covered in another talk. So this is kind of the thinking around how we designed the Blackwell architecture. And if we look at the core of Blackwell, right, and again, the building blocks, the pieces here, right, that we do in data center are going to be the same building blocks that we're going to want to bring over into RTX, into desktop. And so with Blackwell, we significantly increased, this is the Blackwell Ultra die, I should say, and this is two reticle dies put together with a high bandwidth interface in between them. And the SM cores, we improved the compute density by a factor of 4. And the biggest component of this was through the use of FP4 precision, accelerating that. And then we paired this monster die with almost 300 gigabytes of HBM3 memory. So put this all together, and you could do a lot of local compute. And so we solve the problem locally, and then we scale up through NVLink. And so this is kind of walking through the ecosystem down to the chip problem at the data center. So what about for neural rendering, right? What about for RTX? RTX is our brand for simulation. It's our brand for content creation. It's our brand for gaming. How did we use the same architecture and apply it there, right? And so thinking again about this ecosystem problem, right? What we wanted to do is we wanted to, as Jensen has said, we wanted to bring AI back home to graphics, right? We wanted to do it in a way that not only like made things faster, but it really revolutionized the way these applications were run. And so working backwards to the architecture, right? It's natural that we would pull the very efficient Blackwell core architecture for AI and combine it with 30+ years of innovation in graphics technology. Put the two things together, and then spend a lot of time on the glue, right? That makes it possible for those two things to cooperate and work really well together. And so that's kind of how we landed at RTX Blackwell. And I use this term neural shading to talk about the merger of graphics and AI coming together. Neural rendering, I'm sorry. And so let's talk about neural rendering for a moment, right? Because the first assumption you would make is that maybe neural rendering is about doing the same things we did before, but just faster. And I wanted to kind of just use some imagination and talk about what might be possible. And we're using the gaming example here. So first of all, with neural rendering, we believe that things will be more beautiful. Crossing that uncanny valley, that last mile of the uncanny valley, is a non-linear project. We think it's going to take something like 10, if we use traditional techniques, it would do something like 10 times the amount of compute, maybe take 10 times the footprint with all the art, and a lot more developer design cycle time. We're not going to get there through brute force, and we think we're going to get there through neural rendering. And Nvidia has shown technologies like neural texture compression and neural materials, like at SIGGRAPH, that are already demonstrating these kinds of 10x kinds of amplifications, right? So the first thing is more beautiful worlds. Then more smooth and responsive gaming would be the second piece of this. And we've seen this with DLSS4, where on a 5090, you can take some of the highest end path trace content, use DLSS4 to do frame generation and super res, put those things together, where we're generating 15 out of every 16 pixels you see on the screen, running much faster than it would have natively. Now we can use this extra performance that generative techniques give us, and we can apply that to get to the most demanding frame rates, right, for the competitive gamer, or we could hold frame rate constant, pull it back in, and then we can use the energy saved towards battery life. So it's also a mobile strategy as well. The third one is about fun. So fun is it's a hard one for engineers because we don't really know how to quantify it, right? So we want a game to be fun, and this is one of the hardest things that a game developer has to do. One theory of fun that I really like personally is that fun is a reward that your brain gives itself for doing things that are challenging, for doing things that are hard. And that's a very personal thing, right? Because if you're playing a game and it's too easy, then it kind of feels like you don't even have agency in the game. You're just pressing buttons and moving along. And if it's too hard, you get frustrated and give up. You really want the experience to land in your like Goldilocks zone of you, right? That adapts and grows as you play and learn and grow in the gaming experience. And AI has a lot of potential here to help us with this. And last but not least is surprise, right? So I think everyone would love to see conversational AIs in games that aren't so annoying. But what about like 1,000 of these? What if you had a crowd of these agents that were all kind of acting independently, doing surprising things, maybe doing a wave, right, during a sports game, but something strange happens. As long as you control the experience, it could be really cool. There could be a lot of surprise, a lot of imagination could come from it. So we see a lot of potential from this world of neural rendering and what it could do for games. And so now working backwards to the design of the architecture, what are the principles of an architecture you would need to satisfy this? Well, first of all, we're going to be bringing, DL workloads and graphics workloads very close together, and in some cases, we're going to be running them inside the same shaders, right? And so into doing that, we have new workloads that we really need to optimize for efficiency, making sure we're getting to high utilization, not just on our shader cores, but also on our ray tracing cores and our tensor cores. Next, we have to reduce memory footprint. We have to focus on that because developers will use the entire video memory budget for the game, and now we want to add another 10 models to this, right? And so we really need a reduction in footprint so that all these things can work together. Speaking of working together, we have new quality of service challenges. Before, really the goal was to deliver a frame at roughly a 10 millisecond cadence, there, give or take. But now, we might have a large language model that's running concurrently on the GPU that has something like, instead of 10 milliseconds, like 3,000 millisecond deadline, right? So both things are really important for the overall user experience, but scheduling those things against each other is a challenge. And so it was important to think about that as well. And last but not least, as we drive up the density of compute, it's obvious that we have to focus on energy. And so looking at power and energy efficiency was a really important piece of the design as well. So putting it all together, and here is the RTX Blackwell neural rendering architecture with the specs of the RTX 5090, our flagship. We bring in the tensor cores from the Blackwell, from the core Blackwell architecture, and with a focus on FP4 acceleration. I'll talk about why we think that's so important for gaming. We moved to the 4th generation ray tracing cores, right? We don't slow down on graphics innovation. We doubled our ray triangle throughput. We added special functionality for ray tracing. we added a special processor that sits at the front of the pipeline called the AI. We call it the AI management processor, or the AMP, and its job is to manage quality of service. We brought in the Blackwell SM. We optimized for energy efficiency, and RTX 5090 and 5080 were the first GPUs to use GDDR7 memory. So that's kind of that's the nutshell of how we got down to building the chip. Now let's get into some of the details. And I'll start by looking at the SM here. So the Blackwell SM has a lot of optimization and craftsmanship work, but the two pieces that I'm going to talk about today, right, is first the tensor cores, which I'll go into, and why moving to the FP4 in the tensor cores was so important. And the second thing is we doubled our integer throughput. And our integer throughput was actually a very important piece of efficiency for neural rendering. So why would that be? And so I'm going to use this example here with shader execution reordering. It also applies with other producer and consumer models like work graphs. But the idea here is here we have a path tracer, right? We're starting with a fully packed warp of work, and we start to diverge as we do successive bounces, right? And our warps and things start to become incoherent, and we get to a place where when it's time to do let's say a neural shading operation, everything, only a few threads are working on the same material at the same time. We cannot get high efficiency of our tensor cores. And so we introduced this block called the shader execution reordering piece, which is a combination of hardware and software, where at a certain point in the pipeline, right, we queue in the work, we reorder it, and then we queue it back out. And we do so that we can fully pack the tensor cores, fully pack the RT cores, right, and optimize the shader cores as well. So that gray piece is doing sorting, it's doing queuing, addressing. There's a lot of integer math in there, right? And so this is where doubling our integer throughput became so important. It allows us to keep this big 5090 fully fed, or to just spend more cycles or more compute doing better sorting so that we get even more coherent results, right? And so it's useful for both things. Coming back to FP4, so NVIDIA's talked a lot about FP4 already. When we're thinking about models in real-time graphics, there's a three-way trade-off, right? Or a three-way decision point you have to make. You need your models to be accurate and produce great results. Otherwise, you would stick with traditional techniques. Second, it needs to run fast, right? You can't be 10 times slower than another technique would have taken. And third, it needs to be compact, right? We need to be conscious of memory footprint. And we believe that for real-time graphics, FP4 is going to be a great optimization point. For accuracy, it has a much higher dynamic range than integer 4. And with the right pre-training quantization techniques, you can get very accurate results, and I'll show a result on the next slide. In terms of performance, we have twice the throughput of the Ada tensor cores, which had FP8 precision, and we do so at half the footprint for the weights, right? And so combining that all together, it's a really nice optimization point for real-time graphics, and so we expect to see a lot of the models using FP4. In this example, we're showing this is the Flux image generation software from Black Forest Labs, right? It's a diffusion model, and with the FP4 model, right, we were able to achieve pretty much the same quality results, and it's on this image and on many images that were tested, and we're able to do it at 3 times the performance of the baseline FP16 model, and do it at under half the footprint, right? And so, our RTX lineup goes from 5090, but it goes all the way down to GPUs with much smaller frame buffers, and so all these 3 things together is really important, and we're pleased with the results. Next, we move on to memory, and so for the 5090 and for RTX Blackwell, we moved to GDDR7. Nvidia was instrumental in the design of GDDR7, and we were the first to adopt it. And so GDDR7 has much higher data rates than GDDR6, and does it at higher efficiency and lower energy. And it does this, and the innovation in GDDR7 is something called PAM3 signaling technology, where instead of with GDDR6 there are 2 voltage states, or PAM4 in GDDR6X there's 4. With PAM3 there's 3 states, right? And so that allows you to deliver 1.5 bits per clock. But because the signal to noise ratio of the PAM3 is so much higher than PAM4, it allows us to do so at a much higher frequency and also run it at a lower voltage, which is where you get both the bandwidth benefits and the energy savings. So. I'm I'm going to talk a little bit about quality of service now, jump to that topic, right? And so quality of service has always been important to real-time gaming. You need a smooth experience. And it's always been about two things. It's been about smoothness and responsiveness, actually, right? And so smooth is that you get a consistent frame rate. You don't get these stutter effects. And responsiveness is when you make a motion, right? You see the response on the screen. But in general, before today, right? It could mostly be solved by better performance, faster frame rates. You get a more responsive experience. You also have time to pace better and get a smoother experience. And so that was the yesterday. But now let's just introduce a really simple example of a large language model with a long context, right? You can imagine a digital avatar on the game. So that arrow that you see at the top there, that's what I call the uncanny valley of digital avatars, right? It's the time from when you ask it a question and that avatar sits there, and you've probably seen this. It sits there and it nods at you, and it's thinking, and it's going to give you a response, and it takes 3 seconds, and then finally something comes out, and it's really awkward, right? That's the uncanny valley that we would like to, for quality of service, we'd like to pull that arrow in. Once the response starts coming, right? Once we've got that time to first token, then the subsequent tokens just need to run at the rate of human speech, and that could be 4 tokens or 8 tokens per second, something like that. And we could probably make that part run a little bit slower, and so we can play some trade-offs here. And this is what the AMP processor is going to excel at. It's a RISC-V core that sits at the front and is able to talk to the rest of the GPU, schedule work, make sure that the right work is happening at the right priorities on the machine. And in this example, what we've done is, right, we've squeezed in that time to first token, that awkward silence. We've stretched out the subsequent tokens while still staying with it to meet our threshold of 4 or 8 tokens per second, whatever it is. And then what we've used is here we have frame rendering, and then we have DLSS frame generation. We use the increased performance to create some gaps and do both things. So we evenly pace the frames, and we try to get the best of both worlds. And these are the kinds of scenarios that the AMP processor is able to solve. Let's take it a little bit more complicated, a lot more complicated, right? And go back to my first slide, this vision slide. And instead of just running, one LLM in a game, let's think about this whole neural gaming scenario, where in the green we're doing path tracing, we're running neural rendering algorithms, we're running DL super res, we're doing DL frame generation, and all of this has to run at 10 millisecond deadlines, so it has to run really fast. So for sure, these models and this engine, all of that work is going to stay resonant in your video memory, right? It has to, because we don't have time to stream it in and out. Now in the blue, we're going to do all this other stuff. We might have those 1,000 thinking agents in the crowd. We might have an AI co-player, right? That's your ally in the game. You might have some kind of world simulation. And these models will also take a lot of memory. But because their deadlines are 3 seconds or 5 seconds, right, we're able to stream them in and out. And we'll use the benefit of that PCIe Gen 5 has gotten pretty fast, right? And so we can use this little carve out. And as long as we schedule the streaming double buffered with the running of the blue, and then give enough time for the running of the green, we can get this all done and do it right. But it's a complex scheduling problem, and this is where AMP is really this is the big scale problem that we're really after here, right? In terms of doing all these things at once on the GPU. Okay, so I've talked a lot about gaming and desktop and this neural gaming scenario. I'm going to talk for a second about mobile gaming. So this was actually a pet project of mine that I got pretty excited about, that we started some years back, and I was on an airplane playing Civilization on an old laptop, and the thing lasted for 2 hours, and I was like, I thought that discrete GPUs could do better than this, right? And so I really wanted to see what we could do for battery life, and what it turns out that right, as I said it before, is that frame generation is not only faster than normal rendering, but it can also be more energy efficient. If you lock to a frame rate that's acceptable to your battery use case, and in discrete GPUs, you're going to want to pack the work in and get it done fast, you can race to an idle state and save a bunch of leakage. And so combining DLSS frame gen with a focus on efficient time to idleness was a component that especially for notebooks, that we focused on in Blackwell. And so we were able to achieve something like 10 times faster core railgating than previous generations, moving a lot of logic from a software loop into hardware. And similarly with GDDR7 memory, we're able to get 100 times faster time to self-refresh. So putting that all together with and your mileage may vary depending on how demanding the workload is, but we've observed up to a 2x reduction in overall GPU power, which can go directly to battery life. Now we've talked about desktop, we've talked about notebook. In my last minutes, right, I'm going to talk a little bit about enterprise, because Blackwell RTX is also in the enterprise, in the RTX Pro 6000. And in the enterprise, scalability is really, really an important piece, right? Because you're going to run workloads that are small, but still GPU accelerated. You're going to run really big ones, but you have one size fits all. And so multi-tenancy and isolation are a big deal, right? And so Nvidia introduced multi-instance GPU in previous generations, but it was focused on compute, right? The ability to partition the GPU into 1, 2, 4 virtual GPUs and isolate them such that they appear to the operating system as separate GPUs, right? And so in previous generations, that was all compute. In Blackwell, we now support universal MIG, which allows us to also run 1, 2, 4 graphics instances or graphics plus compute instances, something hybrid, right? And we do that by partitioning the SM cores, partitioning the memory system, including physical memory. And then for the blocks at the front of the chip that are, usually there was one pipe feeding the rest of the GPU, we replicate those so that we have fully isolated instances. And so let's take a look at how this plays out. In this example, what we're trying to do is serve up 4 instances of Cyberpunk, but we're doing it at mainstream settings at 1080p resolution, right? So it's a pretty modest setting for the largest discrete GPUs we've ever built, right? And so when you run, if you were to serve up these 4 instances, the simplest thing you could do is just time slice it, right? Do 1, 2, 3, 4, 1, 2, 3, 4, and we'll call that 100% performance, right? I don't remember what the actual frame rates were. Now, if we partition into two-way MIG, right, and we time slice 2 ways on each one to get those 4 instances served up, we now get 152% the throughput of when we were just time slicing on the machine. And this is kind of saying Amdahl's law can be your friend, right? When the workload is too small, you can squeeze things down into a smaller size, and things get more efficient. And so somewhere between 2-way and 4-way, where we get even 160% scaling, right, is that really efficient size for this particular workload. All right, so let's wrap it all up. So I've talked about Blackwell. It's one architecture that solves these kinds of 10x problems from the data center down to the desktop. For the data center, it's about scaling to serve the needs to treat the entire data center as one compute block. And for RTX, it's to bring AI and all of its benefits home to revolutionize graphics, where it came from. We're going to do this by pulling in the Blackwell core architecture, merging it with graphics, and focusing on performance, focusing on memory footprint, on quality of service, and on energy efficiency. So I'm really excited to go back to that first chart, that timeline graph, a couple of years from now, and see what breakthrough was enabled by this architecture. Thank you.
Thanks, Marc. Time for questions. Maybe we start with one on Slack.
Yeah, thanks for the talk, Marc. So I don't do graphics. I don't play games, and I don't do graphics, but I'm communicating someone else's questions, so try to help me out with this. Tsao from Microsoft is saying 2 questions. Do any neural rendering workloads, such as denoise, upscaling, frame generation, do any of those use your NVFP4 data type?
Good question. There are algorithms out there that are using our NVFP4. Our DL SuperRes is not, and I think that's about all I can say for that question. So.
Okay, and then if I can continue with that one, do any of the neural rendering workloads need hardware accelerated motion detection, or are they all just neural based kind of dealing between temporal frames?
Yeah, that's an interesting question as well. And in a previous generation of DL frame generation, where we were using hardware accelerated motion detection, in our latest DLSS4, right, where it's a purely transformer based architecture.
Cool. Okay, thank you.
Thank you. Can we start with a question on this side?
Hey, thanks for the great talk. I'm Soham from Qualcomm. So it seems like you're basically merging 3 different types of workloads here. One is LLMs for NPC conversations, for example. The other is neural radiance field or neural splatting. And the third one will be traditional rendering, right? And ray tracing and so on. Seems like that adds a lot of complexity to the driver/compiler stack. Can you comment a little bit on how much of an overhead that this Blackwell plus RTX brought on that?
In terms of driver overhead, it's a good question. I don't think that there is that much overhead in that part. The heaviest part of graphics driver overhead tends to be that render loop, right? And in general, some of these neural techniques, for example, DL frame generation is a great example of reducing driver overhead, right? Because for every 2 frames or 4 frames now, you're generating 3 out of every 4, right? You don't need a full loop, so the amount of driver overhead can be minimized.
Okay, I see. Thank
you.
Yeah.
Oh.
Yeah, I immersed in eclectic systems. So we actually built a little avatar using all your libraries. So that was pretty cool. Okay, so here's my question. We're doing some rendering for the moon, right? And in that model, accuracy really matters because we're using the rendered images to generate essentially training data that we can then go back and then apply to navigate on the moon. You don't want to lose a $200 million mission, right?
Sure.
So in that case, it's not a game. It's really mission critical. You're building a digital twin of a rover and a lander,
Yep.
right? So in that context, one of the biggest challenges we have is when you're landing on the moon, you have this regolith that goes up. That's a fluid dynamic problem. It's electrically charged. So we have to simulate that, right? So and then we have to render it, right?
Yeah.
So when we render it, typically the RT cores don't really help, right? I'm really wondering if the neural cores will help, because unless we train it on real imagery of the moon, and then we use a lighting model like the HAPQ lighting model for the moon. So this is great if you're doing path tracing, but if you're doing volumetric path tracing, have you tried anything by doing neural rendering for volumetric path tracing? And do you think that we'll be able to use something like that where the actual images have to be accurate, not just look good?
Yeah, I mean, that's a fantastic question, and I'm not going to evade your question. I think what I would like to do is pass you on to our research team so we could ask it that way, but it's a great question. Thank you. Yeah.
Hi, Shashank from UC Berkeley. So orthogonal to denoising methods, ray reuse, like Arista or neuroradiance caching are also becoming quite popular. How much of these algorithms are, say, coarse-grained accelerated in the sense that big chunks of the algorithm have separate paths in the hardware, versus how much of it is fine-grained accelerated in the sense that it is, for example, implemented in Unreal Engine's Lumen, just accelerated by RT cores and tensor cores?
Yeah, I think your question is more about the design of the engine, right, than the design of the hardware, right? Like that if I'm thinking through an engine that would use like ray reuse techniques like you're describing, right? Like it's more in the implementation details, right? Like do you have a dense path of traversal? Those are going to go to the RT cores. Are you using neural techniques, right, to infer the importance and things like that?
My question is more in the direction of how they're mapped into hardware itself, in the sense that are these algorithms sort of crystallized in hardware in the sense that big chunks are directly accelerated with dedicated paths for these algorithms in hardware, or are they implemented in software where general purpose parts of these algorithms are accelerated with these accelerators?
Yeah, I mean, I think these parts are accelerated in the ways you expect through the API levels exposure to the RT cores, right, and the way that the Nvidia's like ray tracing unit is implemented, right. At that granularity is the block level, but there's no like RTX DI block sitting in the hardware. If that's your answer to your question.
Makes sense. Thank you.
We'll take one last question.
Hello. I'm Lux from Berkeley. I want to first thank you for the great talk, and it's great to see so many flops in 5090s. I guess my question is, when it comes to having more AI capabilities, I think we can all sort of understand the need for this in a data center context, but whereas in a desktop, like gaming graphics context, I think still a lot of people are sticking to like 3060 or even like 1060. So when do you foresee this paradigm shift where games will be heavily dependent on AI and require a lot of flops, and we would all need to swap to this?
Yeah, I mean, I wish I could predict that. I mean, and I hope it's sooner rather than later. I think you are starting to see things like with those 1,000 agents problem, for example, right? 1,000 agents requires a lot of flops. even if they're only thinking once every few seconds, right? But you can see already like Epic is talking about agents with the new Unreal, right? And so these things are starting, they're starting to be traction, right? And neural materials, right? With you know, the Nvidia's technology also starting to gain traction. How fast it accelerates, my guess is as good as yours, probably.
I see. On a related note.
Sorry to interject. Maybe we should take this discussion offline in the interest of time.
Happy to answer more on Slack, though.
Thanks.
Thank you.
Thank you.
Yeah.
Let's thank the speaker.
Yeah.
So now on to the last talk of the session. This is on SoCs for augmented and mixed reality devices. We have two speakers again for this talk. Ohad, who leads algorithms and architectures for silicon accelerators at Meitav's Reality Labs. Before Meitav, Ohad started and led camera application processors at Zoran Microelectronics, and he was CTO at Heptagon Micro-Optics. Jay is a 27-year veteran of the semiconductor industry. He's worked at HP, AMD, and Microsoft prior to joining Meitav, and he leads the SoC architecture team in the Reality Labs Silicon Org. Now over to our speakers.
Hello, everyone. It's great to be here. Pleasure. Thank you. Word lock rendering is a technology that is part and required in order to render augmented objects and blend them into the real world scene. And in this talk, we are going to talk about the principles of how it works and describe purpose silicon, specialized silicon, that is implemented in the Orion AR glasses. This is the Orion AR glasses that were introduced last year. It's a development kit. It includes the glasses themselves with display, of course. There is a compute pack that is connected wirelessly to the glasses, and it's meant to offload some of the compute. And a wristband that senses, it's an EMG wristband for essentially human glasses interaction or control. One thing to remember is that the TDP, the power that we have to work with in these glasses is about an order of magnitude less than the power in a smartphone for the silicon. So everything has to be taken in the context of very, very low power. These examples are coming to explain what is head lock rendering versus word lock rendering. So if we look at this scoreboard, for example, this you can imagine is basically staying with you as you move your head, and therefore it is head locked. But this donut is actually a virtual object that sits on a real world object, and we want that donut to stay there, to stick there persistently as we move, as if it's a real object. So it can go outside the field of view and back inside the field of view. And this is word lock rendering. This is word lock. Here it's kind of the same thing. We can put, for example, tags on some of these. If the tags stay on the real world object as we move, it's word lock. If it's this target goes with us, it's head locked. We'll see a few videos that come to demonstrate that. So this is a real room. Everything here is real except for the cat and this avocado. It is being rendered from the user's point of view. And you can see that, first of all, the cat is word locked. So it's as if it's really there. And the other thing to notice, part of word lock rendering, is that the cat is occluded. Parts of the cat are occluded by the desk, and the cat itself is occluding the sofa, as if it's there for real. All of this needs to be calculated in real time, by the way, and we're going to talk about it. That's why we need custom silicon to do that. Okay? And the last example is a real-world example. Somebody is training on a stationary bike. Everything here in this garage is real. except for this screen. It is actually virtual. You can see that the screen is obscured or occluded by this punching bag. And that is a real use case for glasses. There's also hand tracking here that is used to interact with the object. And we will talk a little bit about that as well. Okay, so the principles, the algorithmic principles in order to make all of this working. First of all, we need to calculate the head pose in 6 degrees of freedom. And this calculation is required in order to later be able to compose the scene from the user's point of view. The next thing is a depth image of the scene, which means for every pixel in the scene, we have the RGB and the Z, or the distance from the point of view of the user to that pixel. The next phase is to render the virtual object, and then compose the scene, the virtual object onto the see-through image with the proper occlusions. Once we've composed the scene, we can add hand tracking. Hand tracking is a case where we use them both as occluders, but also for potential interaction, gestures, and interacting and controlling the experience. And there is also audio spatial rendering. Once we know the point of view and the head pose in 6 degrees of freedom, we can also control the audio for a more enriched and full experience. 2 things to remember as we go through the architecture are the KPIs, the motion to photon. This is the latency from when the head moves or the scene moves until it actually being displayed. It's called motion to photon. And that latency needs to be very, very short, okay, within milliseconds. And of course, the other one is the power consumption. We are working with very low power consumption. I said about an order of magnitude less than the silicon in the phone. That's both for battery life and for heat dissipation. So this is the algorithmic block diagram. On the left side, we see the inputs, IMU, camera sensors, and depth sensors. This is the compute, and here we see the output. So we're starting with head pose. We need to calculate the head pose. Essential tracking comes from the IMU, the inertial unit, but those inertial units are, A, they are not accurate, they tend to drift, and they are only relative to themselves. So we cannot really rely on them as the sole input for calculating the head pose. We add to that the camera sensors and run an algorithm that is commonly known as VIO, visual odometry, or SLAM, you may have heard the name, simultaneous location and mapping. And these algorithms, they take the camera sensors and the IMU, and they calculate the head pose within 6 degrees of freedom. With it, we also calculate the hand pose. That comes from the camera sensors. And here we compute the depth image. The depth image can be computed either from in a passive way from the camera sensors or with an actual active sensor or a combination thereof. Each one of them has its own pros and cons, and that's a long story in of itself. But the end result is that we would like to get RGB Z per pixel. Oftentimes you get lower resolution and you need to upscale it in different ways. But the end result, again, is RGB Z per pixel. And here below, we are rendering the virtual content, the augment, be it the cat, for example, that we saw before. With all that, we can go here and basically compose the scene, decide which pixel comes in front, which pixel come in the back, where do we actually place the augmented object, and project it to the display coordinates, to the display. We also take the head pose and render the audio for fuller experience. Because in real life, the audio is also a part of the experience. So that's the principal algorithm. And now Jay is going to talk about how this block diagram is implemented within the Orion headset.
Thanks, Ohad. So here's a close-up of the Orion glasses themselves. We're embedding multiple cameras, sensors, plus all the electronics, speakers, microphones, batteries, all into this form factor. And that poses some distinct challenges. So first, we're extremely constrained in power. We only have a couple hundred milliwatts to work with. It's an order of magnitude less than a typical mobile SoC. And the batteries are extremely small. We address this by targeting advanced process nodes. So in the 2020 timeframe, this was 5 nanometer. We limit our usage of DRAM and try to use anti-SRAM as much as possible. We operate at Fmax at Vmin. And then we deploy a really aggressive power management architecture with a large number of power domains. Basically, anything that is not actively being used is turned off. Finally, we deploy various compression techniques comprising both standard as well as custom compression, and this is just to minimize the energy needed to move data as well as the storage needs. Our second challenge is the physical size. We're extremely constrained by the ID, the form factor, and so to address this, we use some creative packaging techniques to minimize overall board footprint. And we also select interfaces to minimize wire count wherever possible. All this results in a distributed compute architecture. By distributing components around the glasses, we can do a better job of thermal dissipation since the power gets spread around. And then there's simply just not enough power budget up in the glasses to run everything. So we have to move that compute to a compute puck. So in Orion, we split the compute between the glasses and the puck. There's also the wrist-based neural input mechanism that we have, the wristband, but we're focusing this talk specifically on the compute required for world-lock rendering, and that's in the glasses and the puck. In the glasses, we have the glasses processor and 2 display processors, 1 for each eye. The glasses processor manages the Wi-Fi connection to the puck, which contains an application processor and a compute coprocessor. How we divide the compute up is really based on 2 principles. First is the latency sensitivity of the workload. World-lock rendering itself is extremely latency sensitive, and we have to manage that latency so that we don't introduce visual artifacts and break the immersion. The second principle is based on system power considerations. For example, is it less power to run compute locally or transmit it over wireless? In this system, we developed 3 custom chips: the glasses processor, the display processor, and the compute coprocessor. So a few considerations when architecting these chips. First of all, unlike traditional mobile chips that burst and then go idle, the world-lock rendering pipeline is constantly running. When a user's head is always moving, so any virtual object we create has to constantly be adjusted so that it looks stable and locked to the environment. We decentralize the control and power management into the various subsystems. We use multiple microcontrollers distributed in the subsystems. And this allows for very low latency and aggressive power management policies because each subsystem can independently control its own power and clock domains. Furthermore, this simplifies workload isolation and security. We can utilize firewalls within the on-chip fabric to prevent one system from accessing the data of another system. This also, decentralization also allows for modularity as we continue to iterate on the best system level partitioning for future products. The decentralization does come at a trade-off because there is a little bit more complex software development and orchestration among all the subsystems. The final consideration is, due to the long lead time of silicon development, we had to lock the architecture of these chips well ahead of the final product definition. With Orion being a 0 to 1 new product category, we were kind of predicting what would actually be needed in the final product. And with such a long lead time, there were bound to be pivots along the way. So we had to maintain hardware optionality and flexibility so that the architecture was flexible enough to adapt to the changing requirements. So let's talk about the chips in a little bit more detail. The glasses processor is the main control center for the glasses. It provides the physical interface to the camera sensors. There are 6 monochrome sensors. These are for the computer vision tracking workloads of VIO SLAM, eye tracking, hand tracking, and depth. There's also an RGB camera input for capturing the user's point of view. The computer vision subsystem contains the hardware accelerators for eye tracking and hand tracking, as well as a small ML engine, because some of these workloads have been now machine learning based. For compression, we have both HEVC, standard encoder, decoder, as well as a custom developed compression that's specifically for our graphics, textures, and surfaces. Audio, as Ohad mentioned earlier, is an important part of creating an immersive world-lock rendering experience. When a virtual object is making sound, you need that sound to be perceived as if it is actually coming directly from that object. So we split the compute of the audio pipeline between the glasses processor and the compute puck. The speakers and microphones are driven by the glasses processor, while the heavier compute of spatialization and rendering is done down in the puck. Security is also an important part of this, and we have a secure root of trust on the chip, and all data going on and off the chip is encrypted and decrypted. In terms of memory, we have a large amount of on-die shared SRAM, and we also have an LPDDR interface that we use sparingly just for data that simply can't fit in the on-die SRAM. There's multiple tens of megabytes of SRAM, and it's shared and accessible by all the subsystems, which is really important to reduce buffer copies and data movement. PCIe is used to connect to the wireless chip, and USB is also available as a wired interface. For the DSI and CSI interfaces, we chose to use CFI over DFI for the physical interface, and that was because that offered fewer wires, so reducing wire count. And to keep the overall package size as small as possible, we integrated the SoC die along with the DDR die and the flash die, all into a SIP package. This chip has 2.4 billion transistors and 27 power domains. There are 2 basic distinct data flows that are happening on the chip for world-lock rendering. First is the display path, which is shown with green arrows. The rendered content is received wirelessly from the puck. This is then HEVC decoded, and then we re-encode it using our proprietary graphics compression and send that over MIPI DSI to the display processor. For the camera sensor path, all the sensors are aggregated, collected, and either forwarded or processed locally. For eye tracking and hand tracking, which can be processed locally, the computer vision subsystem performs that processing. The IMU is also processed here. And the results are sent to the display processor using I3C, as well as back to the puck over wireless. For any sensor frames that have to be processed solely in the puck, we HEVC encode those and transmit them wirelessly down to the puck. Move on to the display processor. We have 2 of those, one for each eye. The display processor performs the reprojection and display corrections before outputting the pixels of the display backplane. Reprojection, also known as time warp, is a key function to world-lock rendering to keep that motion to photon latency low. The graphics content is received over to the DSI interface, and we use DSI command mode with a proprietary custom-defined packet format for this transfer. The latest pose information comes over I3C from the glasses processor and is then used by the reprojection engine to make adjustments to the frame. Hand occlusion is also applied from the hand pose. And after the reprojection and occlusion are applied, the processor performs a number of display corrections: chromatic aberration, waveguide non-uniformity, dead pixel, and dithering. There's no external memory on this chip, and all data remains in on-die SRAM. There's also a custom parallel I/O interface to the display backplane. There's one for each color each color micro LED. This chip gets co-packaged with the display backplane, and that's to keep the interface power low, as well as, again, to reduce board footprint. And this chip has 1.1 billion transistors and 9 power domains. Finally, we go to the compute coprocessor. This is located in the compute puck, and it's paired to a high-end mobile application processor. The coprocessor supports full computer vision processing for VIO SLAM, hand tracking, and depth, which are all key to world lock rendering. The computer vision subsystem can further handle the VIO processing for both the glasses camera sensors as well as local sensors attached to the puck itself. This allows for 6-stop tracking of the puck by itself. Additionally, there's a relatively large ML subsystem to support workloads such as depth densification and the rapidly emerging AI use cases. Audio compute is done in the puck, and that's the spatialization and rendering that I mentioned earlier. Since this chip's main job is compute, there is higher DRAM utilization compared to the other chips, and so we added a system cache to help reduce that DRAM bandwidth. PCIe and USB interfaces are available to connect to the application processor and to the wireless chip or a wired interface. And we also have MIPI DSI as a low latency path to receive graphics content from the application processor. The die gets co-packaged, again, with the LPDDR dies to reduce package size and footprint. And this chip, being the main compute one, is the largest of the three at 5.7 billion transistors and 76 power domains. Okay. For the world lock rendering data flow, the rendering is done by the application processor, it's 3D GPU. That content is then sent over MIPI DSI and received by the coprocessor. We then HEVC encode it, as well as we have a separate custom alpha channel encoder to efficiently compress the alpha channel. This is then encrypted and transmitted wirelessly to the glasses. For the sensor data coming from the glasses, that's received over wireless and decompressed, and then the frames are processed by the computer vision subsystem to compute the latest pose and depth information. These results are then forwarded back to the AP over PCIe and is used for rendering of the next frames. So putting it all together, here's what some experiences on Orion look like. On the left, you see a virtual game of Pong. Right? The UI elements, the ball, the paddles, these are all world locked, even while the ball is moving through the room. We use hand tracking to control the paddle position. And on the right-hand side, we've got 3 floating windows that are also world locked. They're running different applications. In the middle is there's a video call. And then behind the video call, there's actually the same virtual donut that's world locked that Ohad showed earlier. We needed to develop these custom chips to achieve the world lock rendering in industry-leading wide field of view and a glasses form factor. Off-the-shelf silicon simply just couldn't cut it at the time. This is all made possible by the work of hundreds of engineers inside Meta's Reality Labs Silicon org, our system team, our software team, and our product partners, who all work tirelessly to bring this technology to life. The collective effort has really pushed the boundaries of what's possible, and it's brought us closer to realizing the full potential of AR glasses. And for that, Ohad and I are deeply grateful for everybody who was involved. Thank you.
Thank you for the talk. We'll start with a question on Slack.
This one's from Maya Gokali. They're asking, can you please describe the NIC memory system that's listed on numerous slides, but it's not really shown what the memory system actually is or how it's accessed by compute resources of the NIC?
So I assume they're referring to the...
NOC.
Does it say NIC?
I have just what it says in this question, and I couldn't follow the question either, so I'm hoping it makes sense to you.
I'm guessing maybe they meant NOC.
It's probably about the
They might have meant NOC.
It's probably about the memory system in general.
We have a heavily utilized on-die SRAM, right, to keep the usage of DRAM low, just because the activation energy, access energy of DRAM is so much higher. We have distributed banks of SRAMs spread throughout the NOC, and any subsystem can access any portion of that SRAM. But in general, from a programming perspective, it just looks like a large bank of SRAM that's multiple tens of megabytes.
Thank you. Take one from the room.
My name is Venkata Chivkula. I'm from Microsoft. I would like to learn about the thermal management. Since you're processing lots of data from different thermal camera sensors, how are you handling the thermals?
Yeah, so it's a tiered approach. We have on-die temperature sensors, right, that spread around the chip, and that provides the initial data. We also have some fail-safe, where if we trip at a specific level, we'll actually take drastic hardware actions to shut down, slow down the clocks or possibly shut down. Those are all hardware-based mechanisms. But the more graceful, hopefully we don't have to actually hit those limits. The more graceful method is informing software, primarily running on the application processor, because the application processor in this system is what's running serves as the main brains of the entire system. And notifying software, which will then take software action to also throttle use cases and throttle frequency. So but it's tiered, right? So if software didn't respond fast enough, then we have hardware mechanisms that will also take more drastic action.
Okay, got it. Thank you.
We'll take one from this side of the room.
Yeah, non-quad sensor. So your security domain is a coprocessor, right? Has the IoT and all that. The question I have is that how to expand that to the display processor as well as the compute processor? That's one. The other thing is, do you also protect your IMU and all whatever, the camera and all that? What's the security, I guess the domain covered?
Yeah, so good question. And security is one of those, when I mentioned like evolving hardware requirements, security was a little bit of a moving target. But we do have the capability of securing all sensor data, and full encryption of any data coming off the chip and coming on and off the chip, as well as isolation among the different workloads using the on-chip firewalls. And then even to the display processor, I didn't mention, but there is a crypto HMAC function in there that can also authenticate, right, that the display processor is mated to a Meitav glasses processor.
Is the DRAM encrypted?
So we have the capability to encrypt the DRAM content. It's a product choice whether that's enabled or not. There is that capability, yes.
So it does run, I guess, does it run ARM TZZ or what does it do?
No, this is, these are not running ARM trust zone.
Okay,
it's our own.
Equivalent.
Yeah, it's our own defined.
Okay, there's a secure enclave somewhere.
Right, that's right.
Okay, that's good enough. Thanks.
Thank you. Question from that side of the room.
I'm Shrikant from Google. Very impressive work, by the way, and thanks for a great talk. The question I have is, you mentioned that you had to design the silicon several years before the product. Now that you have the product, would you design the next generation silicon differently? Would you make a different set of choices?
Yeah, we're constantly learning, so absolutely, right? Orion's a dev kit, internal dev kit, and we're learning from that. I can't really go into details, but we're already actively have been working on the follow-on, because ultimately the goal is to convert this from into a prototype to something that is consumer friendly, right? So there are, and as technology improves, right, we can choose. This is when I mentioned the modularity of the workloads, right? As we process technologies get better, we may have higher power, more power budget to run some things, and we might move the partitioning of where workloads run.
Thank you. Can we take one more from Slack?
Yeah, there was a question as whether you considered MRAM for the glasses for lower power.
So MRAM doesn't have enough, so the bandwidth that we still need pretty high bandwidth, right? So our bandwidth needs are higher than what we could get out of MRAM. I will say that memory technology is a key area that we have to continue to look at and invest in, right? In Orion, we're using SRAM and some DRAM, but we continue to kind of focus on this space because there are trade-offs with each of those itself. But MRAM itself, we didn't conclude that to be adequate for our needs.
Thank you. I think that concludes the session. Thank you again for the talk. Now it's time for the break.